Okay, so this is a continuation of our discussion on chapter 3, and this will be about the derivative as a rate of change. So, rate of change, the most common or usually used type of rate of change is the what we call the time rates. When we say time rates, these are changes of a certain quantity with respect to time. An example of this one in physics, we have the velocity. The velocity can be measured through the traveled distance. This is by measuring the traveled distance or displacement with the time needed to travel, divide it with the time needed to travel that distance or displacement. And to take the average, usually the average is uh, S2 minus S1 all over T2 minus T1. But most of the time, we make our initial displacement to be zero, and our time is always or starts at zero usually. So the average velocity is just equal to the displacement divided by the time. But what if you want to determine the instantaneous velocity at a certain time? What's the velocity at this point of time? So instantaneous, we call it instantaneous velocity. To do that, we go back again to the first definition, this one. So the velocity is equal to S2 minus S1 over T2 minus T1, and we can rename that as delta S over delta T. Delta S means change in S, delta T means change in time. And to make it instantaneous, we take the limit of this one and we make delta T very, very small. At that certain point, it's just the velocity at a specific point. And if you remember, this is somewhat similar with our slope before. The limit of delta y as delta x approaches 0 all over delta x, and this is dy dx. This is the definition of derivative as a slope. Here in the velocity, we can also do that because it's similar. So this is also the same as the derivative of the displacement with respect to time. So that's the velocity, instantaneous velocity. It's the derivative of the displacement with respect to time. And if you put the definition of derivative, the velocity now will be equal to the limit. We make s as a function of time, s as a function of time. So this will be s t plus delta t minus s of t all over delta t. So this is the basic definition of the derivative as a rate of change or a time rate. Now, another one is the acceleration. The acceleration is just the change in the velocity with respect to time. So we can also represent it as a derivative. So acceleration is just the change in the velocity with respect to time. If you want the instantaneous, then this will be the limit of delta b as delta t approaches 0. Or this is also approaches 0, v as a function of time plus delta t minus v of t all over delta t. That's the acceleration. In electrical engineering, we have what we call the electric current. Electric current. And electric current is defined as the flow of electron. This is the rate of flow of electron. It's a rate. So it's how much electrons are moving with respect to time. But we don't use electron as a quantity. We use what we call the charge. charge has a unit of 1 coulomb, and it's equivalent to 6.28 times 10 to the 18 power electrons. So if we want to determine the instantaneous current I, and this will be equal to the limit of the change in Q. So we can make this small letter q. So delta q with respect to time as delta t approaches 0. And this is also the derivative of q with respect to time. Later on, from your higher courses, you will discuss this again in the application part. And we can also make rate of change not in terms with the time, not a time rate. We can also make, for example, change in the velocity or change in the volume of a sphere when the radius is changing. This is make the limit as delta r approaches 0. This is just dv dr. Or if you want to the change in the surface area as the radius is changing, and so on. So those are examples of rate of change. We will discuss them more in the application part. Now let's take an example. Let's take example from your module. So this one. A particle moves along a horizontal line. The function s of t gives the particle's position at any time when t is greater than or equal to 0. So s of t is equal to 2t squared as 3t. What is the particle's velocity at t equals 3? So we have here, we want to determine the velocity. Again, what's the definition? It's the limit of s of t plus delta t minus s of t all over delta t as delta t approaches 0. Now, but we want it to be at t equals 3. So what is the velocity at t equals 3? So v will be equal to the limit delta t approaches 0 s3 plus delta t minus s3 all over delta t. So what is s of 3 plus delta t, or s3? First, s3. s3 is, we have here 2t squared plus 3t. So this is 2 times 3 squared plus 3 times 3. And this is 9 plus 9 times 2, 18 plus 9, so it's 27. For s3 plus delta t, this is equal to 2 times 3 plus delta t squared plus 3 times 3 plus delta t. Now expand this one, so this is 2 times 3 squared, 9 plus 2 times 3, 6 delta t plus delta t squared plus 9 plus 3 delta t. So that is s of 3 plus delta t. Now we substitute this one to our formula in the velocity. So the velocity and the limit as delta t approaches 0. So this is 2 times 9. So we have 18 plus 2 times 6, 12 delta t plus 2 delta t cubed I squared plus 9 plus 3 delta t. So this is s of 3 plus delta t. Then minus s of 3. Our s of 3 is what? 27 all over delta t. Then we can simplify. 18 plus 9 is 27 here, minus 27, so this will cancel out. Then we can cancel out delta t, 1, this is 1, and this one. So what will be the remaining terms as delta t approaches 0? So we have 12 plus 2 times delta t plus 3. Then applying the limit as delta t approaches 0, so this will be 0. So what will be the velocity at t equals 3? Velocity will be 12 plus 3, and that is 15. 15. The unit, it can be meters per second, it can be kilometers per hour, miles per hour, and so on. Let's take the next example. 3.1.4, this one. It's almost the same with the first one, but this time we want to determine the acceleration at t equals 3. So instead of the velocity, we want the acceleration. So what's the acceleration? How do you solve for the acceleration? This is the limit of the velocity t plus delta t minus v of t all over delta t as delta t approaches 0. But v of t is not given. The given is x of t. And this is t cubed minus 3t squared plus 7t minus 6. Can we determine v of t in terms of x of t? Yes, just like what we did in the previous example. v of t now will be equal to the limit of x t plus delta t minus x of t all over delta t as delta t approaches 0. So what is x of t? This is x of t. X of t plus delta t. This will be equal to t plus delta t cubed minus 3 times t plus delta t squared plus 7 times t plus delta t minus 6. Then how do we expand the cubic binomial? Note here. A cube plus b cube, or a plus b cube, a plus b cube is this equal to a cube plus 3a squared b plus 3ab squared plus b cube. So from your algebra, that is a plus b cube. So this will be e cube plus 3t squared delta t plus 3t times delta t squared plus delta t cube. Then minus 3 times t squared plus 2t delta t plus delta t squared. Then plus 7t plus 7 delta t minus 6. Then simplify further. We can distribute 3 here. So minus 3t squared minus 6t delta t minus 6 delta t squared plus 7t plus 7 delta t minus 6. And we can just copy this one and we subtract x of t. So what is x of t? It's t cubed. So we just subtract minus t cubed minus 3t squared plus 7t minus 6. So what will be the difference? T cubed here will cancel out. What else? 3t squared minus 3t squared minus 3t squared. Then we have 7t minus 7t. This is also will cancel out. And negative 6 minus negative 6 will also cancel out. So what will be the remaining terms here? So we have now the limit, the velocity, this is the acceleration or the velocity. The velocity limit of the difference, which is 3t squared delta t plus 3t delta t squared plus delta t cube minus 6t delta t minus 6 delta t squared, then plus 7 delta t plus 7 delta t all over delta t when delta t approaches 0. So we can cancel out delta t. This is 1, and this is squared. Cancel this out. So it will become 1, and this will cancel out. So we have now the limit delta t approaches 0 of 3t squared plus 3t times delta t plus delta t squared minus 6 times t minus 6 times delta t plus 7. Then we apply the limit. This will be equal to 0. This will be equal to 0. And this is also equal to 0. So what will be the remaining terms? What's the velocity in terms of t as a function of t? So v of t will be equal to 3t squared minus 6t plus 7. Now we know v of t. We can now solve for the acceleration. Acceleration at t equals 3. So a equals the limit of v of t plus delta t. So I'll just directly put it here. So 3 times t plus delta t squared minus 6 times t plus delta t plus 7. Then minus v of t. This is 3t squared minus 6t plus 7 all over delta t as delta t approaches 0. Then take the limit or simplify first. So what do we have here? Expand this again. So this will be 3t squared plus 3 times 2, 6t times delta t plus delta t squared minus 6t minus 6 delta t plus 7. Then minus 3t squared plus 6t minus 7 all over delta t. So we can cancel out now 3t squared, 3t squared. Then minus 6t plus 6t. Then I forgot to put 7 here. Why is it 3? 6 delta t. This should be 7. So it will cancel out with that one, 7. Then cancel out delta t. This will become 1. Cancel out delta t and delta t. So what will be the remaining term? 6t plus delta t minus 6 delta t squared. 1. Okay. Then apply. We can now apply the limit. What will be the limit? This will be equal to 0. And what will be the remaining terms? So we have acceleration is 6t minus c. So when t equals 0 at t equals 3, what will be the acceleration? Acceleration will be 6 times 3 minus 6, or that is equal to 12. Okay, and for the last example, Example 3.15. Determine the rate of change of the volume of a sphere with respect to its radius when the radius is equal to 4. So the volume of the sphere is changing while the radius is changing. So what's the volume of the sphere? This is equal to 4 over 3 pi r cube. Then if you want to determine the change in the volume, dv with respect to r. So this is just equal to the limit of the velocity or the volume r plus delta r minus v sub r all over delta r when delta r is approaching 0. So we have here, this is v sub r in terms of r, v sub r plus delta r will be equal to 4 over 3 pi r plus delta r cube, where this is 4 over 3 pi times r cube plus 3r squared delta r plus 3r delta r squared plus delta r cube. Then we need to subtract this one with 4 over 3 pi r cube. So what will be the result? So the result, this will cancel out and this will cancel out. So what will be the remaining terms? At the numerator, we have 4 over 3 pi. So r cube will cancel out. So we have 3r squared. 3r squared delta r plus 3r delta r squared plus delta r cube. And we divide it with delta r. We can cancel out delta r here. This will become 1 and this will become 2. So we have here 4 over 3 pi and the remaining 3r squared plus 3r delta r plus delta r squared. And if you apply the limit as delta r approaches 0, this will become 0 and this will become 0. Then this will cancel out here. Then we have now the velocity or the volume, change in volume with respect to r will be equal to 4 pi times r squared. When r is equal to 4, so the volume with respect to r, when r equals 4, 4 pi times 4 squared. And this is equal to 64 pi. So the change in volume with a 1 unit change in the radius will result to a 64 pi cubic units. So that's the meaning of the change on the volume with respect to the change of the r or the radius. So this is our lecture part 2 of chapter 3, and it's about the rate of change. We will discuss more about this one in the applications. Later on, we will also in the next sections we will derive the formulas so that we will not go through this very long solutions. Later on, we will derive the formulas to simplify or to shorten our solutions of taking the derivative of functions without using limits. Okay?